Your phone is getting smarter, but there's a hidden problem. AI still thinks one word at a time. Every instant summary, smart reply, and notification assistant has to run on a tiny device with limited memory, limited battery, and no room for cloud-level computing. So how can on-device AI become fast enough to feel truly instant? In this video, we'll break down the core bottlenecks slowing mobile AI, why autoregressive models struggle on phones, and how new approaches like draft and verify decoding and multi-token prediction could change everything. We'll also look at memory savings, faster inference, and why predicting multiple tokens, or even multiple branches, in parallel may be the key to the next generation of private, real-time AI on your phone. Let's get into it.
Hey everyone, welcome to The Explainer. I'm seriously so excited to share this one with you today. We're going to look right under the hood at some truly brilliant engineering from Google. We'll be breaking down exactly how they made artificial intelligence significantly faster, much more efficient, and far less memory hungry directly on your smartphone. We're talking about the absolute magic behind multi-token prediction. To kick things off, let's ground this in something we all experience every single day. Think about it. How exactly does your phone summarize a massive flurry of notifications instantly without completely killing your battery life? Or how does it proofread a long text message in the blink of an eye? On devices like the Pixel 9 and the Pixel 10, these incredibly complex tasks are happening right there in your hand, without ever sending your private data off to a cloud server. But to make that user experience actually feel like magic, the backend engineering has to overcome some massive physical hurdles. Okay, let's dive into this. Section 1, the on-device AI bottleneck. To understand the core challenge of running powerful foundation models locally, we really have to contrast two very different worlds. Usually, when we think about AI, we picture these massive cloud server farms, right? In the cloud, you have vast processing power and essentially an unlimited energy budget. But edge computing, running AI in your pocket, operates under incredibly strict energy budgets and, crucially, hard memory limits. You can't just throw more RAM at the problem. Compounding those physical limits is how language models actually work in the first place. Standard language models generate text autoregressively. Fancy word, I know, but it just means they process and output one single word, or token, at a time. It's a strictly step-by-step process. Imagine a slow, incredibly meticulous typist who literally has to finish typing one key before they can even think about hitting the next. This creates a severe bottleneck. It underutilizes the phone's processing power while simultaneously straining its memory bandwidth. The result? A sluggish user experience and a rapidly draining battery. So, how did engineers initially try to speed up this sluggish typing process? Well, that brings us to Section 2, the speculative decoding strategy. Speculative decoding essentially splits the job into two parts. First, you have a draft phase. A smaller, much faster approximation model, which we call the drafter, takes a quick guess at the next few tokens. Then, you have the verify phase. The large main model processes those guessed candidates in parallel. Think of it like a super eager, fast-typing intern writing up a quick rough draft, while the senior boss reads over their shoulder, verifying the work in parallel just to save time. If the boss agrees, they keep the draft. If not, they scrap it and start over. Now, that intern and boss setup is definitely faster than the boss doing all the typing alone, for sure. But it comes with a massive memory-hogging flaw. And that flaw leads us right into Section 3. Enter multi-token prediction. Solving that flaw brings us to Google's groundbreaking new architecture. And this comparison is where things get really fascinating. The old way relies on a standalone drafter. Running a completely separate standalone drafter model means it actively competes for your phone's extremely limited RAM. Plus, this standalone drafter is essentially flying blind. It's predicting the next words based only on the text history, without seeing the deep semantic context the main model has already figured out. Google's solution is the integrated MTP head. Instead of a separate memory-hogging drafter, they appended a lightweight multi-token prediction head directly to the final layers of the main model. It leverages the high-dimensional work the main model has already done. So, the absolutely crucial point here is how they actually attach this new head without breaking the model, leveraging what's called the frozen backbone advantage. Google takes a fully trained Gemini Nano v3 model and completely freezes its weights. They only train the newly attached MTP head to predict future tokens. Because the main backbone is frozen, this is strictly an efficiency optimization. There is zero, literally zero degradation in the base model's capabilities or its safety alignment. Actually, because incorrect drafts are simply tossed out during verification, the final text output remains bit for bit identical to what the original model would produce. It's a pure speed upgrade with full backward compatibility, which is just wild. Now that sounds great for speed, right? But what about the physical constraints we talked about earlier? How do we actually save mobile memory? Because here's the hidden trap. Even if you share some weights between the models, independent drafters usually cause this nasty double tax on your phone's dynamic memory. They have to generate and maintain their own completely separate context history. To avoid that double tax, the engineering team had to get incredibly creative. Let's look at how they did it in Section 4, Zero-Copy Memory Magic. Here is the true hero of this whole story. Instead of the MTP head creating its own separate memory history to guess the next words, it's designed to cross-attend directly to the main model's frozen key value cache. In plain English, the drafter directly queries the rich memories and context that the main backbone has already computed. It doesn't duplicate the work, it literally borrows the main model's brain state. That zero-copy design yields two massive efficiency gains for us. First, it entirely eliminates what's called drafter prefill latency. Because the MTP head is using the main model's existing cache, it requires absolutely zero additional time to process the initial prompt. Second, it drastically reduces the runtime memory footprint on the device. So what's the actual number? How much memory does it save? 130 megabytes. By ditching separate lookup tables, redundant attention processing, and specific tuning parameters, this zero-copy architecture saves 130 megabytes of precious RAM per instance compared to a standalone drafter. On a mobile phone, freeing up 130 megabytes of memory is an absolute game changer. But how does all of this back-end wizardry actually translate to the person holding the device? That brings us to Section 5, Real-World Pixel Performance. And this brilliantly illustrates the real-world impact. When we look at the average additional tokens correctly predicted per pass, a standard base model gives you 0 extra tokens. It's that super slow typist. A standalone drafter might give you about 1 extra token. But the MTP head? In production workloads like AI notification summaries and proofread, it's correctly predicting nearly 2 extra tokens per inference pass. Because the MTP head has access to the main model's richer, deeper representations, it is incredibly accurate at predicting syntactic patterns and following complex instructions. That accuracy translates to this massive number right here, 50%. On Pixel 9 and 10 devices, using MTP results in a speedup of 50% or more, depending on the task, compared to using standalone drafters. Because it's generating text so much faster, it spends far less time waking up the phone's heavy processors, and that means significantly less energy consumption and a much, much better battery life for you. Which leaves us with this provocative thought to wrap up our explainer today. Google isn't stopping here. If we can confidently and accurately guess the next few words without draining memory, what's next? Can we train these on-device models to explore entire branching possibilities of language in parallel? The research teams are already investigating ways to handle ambiguous language generation by exploring multiple future paths simultaneously, and even testing verification leniency to speed things up even further. The evolution of edge computing is happening at breakneck speed, and it is absolutely fascinating to watch. Thank you so much for joining me to explore the science behind it today. Keep learning, and I'll catch you on the next explainer.